ไซส์ที่มันใหญ่กว่าอันเนี้ย おはようございます、先生。先生、ありがとうございます。
Hello?
Hello、先生。
Hello?
OK で、聞こえます。
Can you hear me?
Yes, yes,
あ、聞
yes。
こえます。OK。
ありがとうございます。
どういたしまして。うん、元気ですか？
はい。
元気、元気そうだ。顔が元気そうです。
先生もとても元気。
ああ、まあまあね。うん。うん、10時に、タイタイムで10時だから、
10時、1時ぐらいです。
うん。
もうちょっと待ってください。
あ、待ってます。
今、多分、サニタさんと、あと学生さんも北海道の方に行ってるだと思う。
あ、あ、そっ
HIU?
か。あ、待ってよ。あれ、そうだね。そうだね。えっと、何 What is my schedule? What is my schedule? ワークショップ。うん。昨日、あ、違う。今日が22日だから、昨日か一昨日
はい。
来てるんだね。
はい。僕、来週に行きます。
あ、本当？うん。
28から
うん。
ぐらい。はい。
28くらいに来るの？
はい。HIU の方、20、まあ、28について、
うん。
29か30ぐらいにも行きます。
HIU に、
先生はいらっしゃいます？
えっと、28、29、ね、28は午後12時から5時くらいまでは予定が入ってて、
30でも先生、先生次第。
うんとね、3、29はね、空いてるの。
え、29
29
ですか？
日は。
はい。
30日はちょっと、予定が入ってますね。
はい。わかりました。
29日は、えだいたい1日、29日は1日どの時間でも、えー予定を開けら
はい。
れます。
はい、わかりま
28
した。
は夜は大丈夫。
OK。OK です、先生。OK。僕、札幌駅
うん。
の近く、泊まります。
あ、そう。
ホテルが。
札幌駅の近くなんだ。
札幌なんとか、マイステイ札幌エスペン、
ああ、はい、ありますね。
この前の同
うん。
じところですか？
あ、この前もそうだった？
はい。久しぶり日本に、もう
うん。
1年くらいかな。
うん。1年ぶり？
1年ぶりくらいだと思います。
うん。
今回僕は 3泊くらいかな。
3
28、
泊？
29、
うん。
30、31、1日の朝、めっちゃ朝に出ます。
28に来るの？
で、あ多分、
28 に。
来るのは28
うん。
朝に。
で、
で、まあ多分朝ではないですけれども、昼くらいについてで、
うん、9月1日に出発、タイに帰る。
そうです。
僕、9
はい。
月1日から東京。
大丈夫。まあ、先生、一日、まあ、半でも、
うん。
何でも OK です。
はい。
まあ、先生
28
次第。
日夜は OK です。29日は一日中大丈夫
OK。じゃあ、
です。
日中9に来ます。
はい。29
はい。
に情報大学来るの？
日中9、
はい。
30くらい来ます。
うん。30はね、僕ちょっと朝からね、札幌で用事があるので、
もうじゃあ、僕、日中9に来ます。30多分、なんとか、HIU とミーティングあるみたいですが、
あ、そ
サニダーさんから
う。うん。
30日来てくださいと。
うん。
今もう多分サニダーさんが、もう HIU かな、だと思う。学生さ
うん。
んと十何人
ワークショッ
ぐらい、
プね。
ワークショップで。
うん。何人来てるんだろうね。
十何人ぐらいだと思います。
うん。
もし先生について、まあ、20ぐらいかな。
学生が12人くらいだったかな。
12人ぐらいかな、だと思う。今
うん。
回先生の方はちょっと少ないですけれども、
うん。
あ
3月まで僕がまだ情報大学の教員だった時に、
ええ、
その辺コーディネートしたんですよ。
じゃあ、10何人ぐらい。
確か12人くらい、学生が12人くらいで、
ええ、
スタッフが4人か5人だったかな。
そうだと思います。
で、
はい、わかりました。ありがとうございます。
HIU の方が予算がないということで。
わかりました。
うん。
今回僕、先生、HIU の方にも行きます。まあ、先生に
はい。
も会いに行きます。ご飯
はい。
でも、食事でも、何でも OK です。まあ、先生の時間次第。僕、札幌駅泊まりますんで。
うん。夜ね、30日はダメだけど、あとは
ええ。
夜は OK です。
だかか日中8夜どうですか先生。
28夜 OK。OK
はい。
ですよ。
ど、どの辺がいいかなと思って。
どっか希望があれば探しますか？
あ、なんでも OK です。先生次第。
でも OK。
札幌駅どうですか？
そうだね、札幌駅の近くがいいね。
なんでも OK です。
うん。
晩ご飯でも。
晩ご
うん、
飯食べますか？
夜ご飯でも、まあ先生次第。まあ夜
夜
で。
ご飯ね。28じゃあ晩ご飯、夜ご飯食べますか？
まあ先生の時間次第です。なんでも OK です。
はい。はい。28ね。OK。29でも OK です。はい。じゃあ、
はい。
後で LINE で僕の予定もう一回、今言った予定、LINE で送ります。
はい。わかりました。ありがとうございます。
はい。
今日もちょっと、今日、新しい学生さんの修士課程の学生さんは、まあ、4、5人くらいに、あ
あ、
このセ
はい。
ミナーが入ってますんで、
はい。
まあ、毎年同じくらいでも
うん。
OK です、先生。少しでも
学生さんが4、5人？
A だと思う。
はい。
多分、他の 先生の方の興味があれば入って
はい。
ますんで。
はい。
あと5分、10分くらい始まりますんで、
うん。
まあ、
はい。
ゆっ
わ
くり。
かりました。わかりました。
今回、
こコーヒー入れてる時間はない
まあ、先生、まあ、なんでも OK です。先生、どうぞ。
の。でも
今回、学生さんのコースなんで、
うん。ちょっとコーヒー入れてく
はい、
るかな。
はい、はい。
今ね、ここ私の家ですから。
おお、なんか研究室っぽい。
私の部屋。
おお、おお、びっくりした。
ちょっと、ちょっとコーヒー入れ
はい、
てくるから5分くらい。
はい、わかりました、先生。はい。
はい。
นักศึกษาน่าจะเข้ามาแล้วเนาะนักศึกษาครับใช่ไหมสวัสดีเจ๊ปุ๊กใช่ไหมเนี่ยไอโฟนเมื่อกี้เห็นรูปเห็นโอ้นี่มา where are you นี่มา oh in laboratory
Good morning, sir. Yes, I'm at lab.
okay thank you very much for your coming and please ask the question for today
Sure. Thank you very much
today
for
was
it.
about the polymer physics but it's not quite easy I but he can speak easy
Mm. Yes, I like to broaden my knowledge because now
yes
I'm working on nanobubble too. So this is very
yes
interesting.
yes it's very good for your to learn many knowledge and apply the knowledge for your research is very important
I see. Yes, sir. Yes, sir. Thank you very much.
because this is your life. Enjoy your life for your the future,
Thank you.
for your future. Not for us, but for your future. It's good,
Yes.
I guess. And if you know the many professor, maybe the next time or for the future, you can go.
Mm. Thank you very much.
Actually, Ananda Sensei, he's cooperate with us more than 10 years already, and we send our student to Hokkaido, and
Mm.
now I'm UTT student now in Hokkaido Information University about 12 students and about four teacher.
Wow, very interesting.
Yes, it's interesting is when our student see the snow,
Oh.
first time snow in his life. Very
Oh,
interesting for
that's cute. That's cute.
not only for the research only, but for life.
Mm,
The life is yours.
yes, very,
Enjoy and
very
have many
experience.
experience.
Yes, yes, very nice experience for it.
But the first step is know the professor from Japan or the know professor from the other countries is like a connection or network. Research network is very important for the research in this moment and the future.
Mm, yeah, I see, I see.
Sometimes
Uh,
you don't need to have many apparatus, but if you know the professor, you can send your sample to his laboratory.
Yes, yes, exactly.
But when I start my research at here, I do like this. I don't have the apparatus or the testing machine, but I know the many professor. This is a strong point. I send them many sample to them.
Wow, I see, I see. Especially with Professor Kiyoshi, that he's
He
working
or
on.
she,
Well, yes, it is
mafia
very
professor.
good.
He is the mafia professor,
Oh, wow.
but he's strong power, very strong, and still strong more than us.
Yes.
He already maybe 81 or 82,
Wow.
but he's still strong. And also today, another Professor Anada also maybe nearly 75, but he's still strong more than us, stronger than us. Because if every years and maybe if every single season he is a professional ski.
Wow. Skiing. Oh my God.
He's still skiing.
Wow, that's awesome.
Today,
Wow.
maybe you can ask the secret of his health.
Oh,
He's
oh
strong.
yeah.
Yes,
That's
he's a
interesting.
very kind professor. But
Mm.
his subject and his research about the polymer physics is not so easy, but he can speak and he can understand. And the most important is the connection, and we know them, we know his team, and also you can ask them about you can ask him about the secret of his health. Why he still ski? He still ski. Now he's nearly 80, maybe I think 75. พี่เต้เห็นแล้วสวัสดีครับพี่เต้
สวัสดีน้องสวัสดีทุกคน
เดี๋ยว
Good morning everyone
เดี๋ยวอนาดาเข้าไปชงกาแฟก่อน
Dr. Roy, how
right
are you?
I'm
เดี๋ยวทัก
okay
ทายอนาดา
I'm
ก่อนก็ได้
okay
พี่เดี๋ยวทักทายอนาดาสักครู่หนึ่งก่อนเดี๋ยวรอแกแป๊บหนึงแก70กว่าแล้วนะ75มั้งแต่แกยังสกีอยู่เลยอ่ะคุยกันอยู่สุดยอ
เขา
ดเลย
กินปลาเขาไม่ได้กินเนื้อกินหมู
เฮ้ยเขากินนะเขากินแอลกอฮอล์กินอะไรด้วยนะเดี๋ยวต้องถามแกเนี่ยไอ้ไอ้เรื่องความลับเรื่องสุขภาพเนี่ยเราต้องเรียนรู้นะ ตอนเราไปเตรียมตอนเกษียณแล้วไม่ทันนะพี่เต้เหลืออีก10 ปีกันเองพวกเราเนี่ย
เขาก็น่าจะออกกำลังกายมากกว่าเรา
ใช่พวกเราออกกำลังแต่ยกแก้วไง
ออกกำลังกายกินปลาอะไรเงี้ยไม่อ้วน
เรา
ไม่
ใช่เรารู้หมดแต่เราไม่ทำ เดี๋ยวเราถามแกเมื่อกี้แกก็เลยบอกว่าวันนี้เป็นของเซมินาร์ของปอโทปอเอกอะไรเงี้ยครับเดี๋ยวรอแกก็บอกแกไม่ซีเรียสอะไรเงี้ยเพราะตอนนี้เที่ยงที่นู่นแกก็เลยขอไปกินกาแฟก่อนเอากาแฟรอสักพักหนึ่งที่แรกผมนึกว่าแกที่แกโชว์ข้างหลังนี่คือห้องแลบนั่นน่ะไม่ใช่นั่นบ้านแกนั่นเนี่ยหนังสือขนาดนี้เลยเหรอผมก็เลยงงเลยอะไรวะนี่ออกมาแล้วเซนเซมาแล้วเดี๋ยวพี่เต้ทักทายแกด้วย
ได้
มาแล้วเซนเซ
Hi.
Hi Yoshi
Another
Hello.
sensei.
How are you?
Hi I'm okay how are you you
Okay.
look very healthy
A little bit.
What
I'm
is
run.
we are talking
Run.
about what is the secret of your healthy and you still stronger than us.
No secret.
No
I
secret.
train. Next
Ski.
weekend, I'll go to a big lake in Hokkaido, Kusharo, Lake Kusharoko.
Marathon?
Oh,
For
Yeah,
marathon?
water,
Work?
open water
Swimming.
swimming
swimming
in the lake.
Oh, leg.
Yes.
Not cold. Now in Japan, very hot.
Japan?
Ah.
But Hokkaido is not hot.
Oh.
Today, cool.
In Kyoto.
In Kyoto, maybe it's very hot.
Because
Kyoto,
I heard the
Tokyo,
news very hot.
Osaka, Honshu area is very hot. But
Last
Hokkaido,
two.
Hokkaido sometimes hot day, but many days recently, especially recently cool. Today temperature. Now my room temperature is 24 degrees
Oh,
here.
good for here and good for beer.
No air conditioner.
Good for here and good for beer.
Maybe
It says, sorry, we are talking about your age. 70.
70, now 70. This autumn, maybe 2 months later, 71.
71. Oh, stronger than us.
Huh?
Stronger than us.
Thank you.
And stronger more than Bunyang.
Bunyang nearly dead. Where is him? Where Bunyang now?
Where is Bunyang?
Maybe not waking up yet. Drinking too much last night.
Every night. Not only last night.
Every night drinking. This is a secret, right?
It's not secret. Everybody know.
But you always might be, maybe this is your secret of your strong.
Laugh and smile. Laughing and smile.
Yeah.
Very important.
Yes. Life is important.
Okay, so
you mean
today
every day we have to laugh?
Huh?
Every day we have to laugh and smile.
I think so. You all every day laugh and drink.
Yes, Professor.
Yeah, drink not too much.
Hello.
Hello.
Long time not see you.
Yes, sir.
Nima is is our PhD student of the course of energy and materials.
Final year now, right, Nima?
Yes, sir. I'm on third year.
Huh?
Okay.
Sorry?
Yes.
The third year of the PhD student. Yes. He's writing the first manuscript to submit the journal the first time of his life.
Good. Okay.
Okay, Sensei.
Okay.
So today, thank you very much for Professor Anada from Hokkaido Information University, or that we call HIU. Is in Hokkaido, near Sapporo. Near Sapporo. It's far from the Sapporo, maybe 30 or 40 minutes, right? Sapporo station. Yes.
20 minutes.
20 minutes, okay. Okay, so today we have a big professor about the polymer physics. Okay, so today is the class of the seminar, and also for the PhD student and also master course student at the first year. So today is not so deeply, but for our student and also maybe some teacher of IMUTT. Thank you very much for your accepting at this lecture, this seminar.
You are
not
welcome.
seriously, like your smile, like your smile, Sensei. Okay. And the final before you closing your presentation, please tell us what is the secret of your good health.
Okay.
Okay, Sensei.
Okay. So I'll show you my PowerPoint. Can I share my PowerPoint?
Yes, you can share now.
うん。
นักศึกษาครับก็เซนเซก็เป็นเซนเซที่ Hokkaido Information University นะครับท่านเก่งทางด้านpolymer physics นะครับแล้วก็พยายามครั้งนี้ก็จะพยายามให้ท่านพูดเกี่ยวข้องกับเบสิกพื้นฐานนะครับเพื่อเป็นความรู้นะครับแล้วก็อีกอย่างหนึ่งมันอาจจะไม่ได้เข้าใจทั้ง100%แต่ว่าผมคิดว่าก็ได้คอนเนคชันที่เป็นระดับโปรเฟสเซอร์นะครับเผื่อนักศึกษาได้ถามคำถามอะไรก็ตามนะครับที่ไม่ค่อยเข้าใจเกี่ยวข้องกับโพลิเมอร์การโพลิเมอร์ฟิสิกส์นะครับมันอาจจะยากหน่อยแต่ว่าผมคิดว่าน่าจะเป็นอีกเรื่องหนึ่งที่น่าสนใจครับนะครับโอเคพอเราส่งนักศึกษาตอนนี้มีนักศึกษาไปอยู่ที่ Hokkaido Information University ประมาณ12คนนะครับแล้วก็มีเซนเซไปประมาณ4คนนะครับโอเคโอเคเซนเซどうぞありがとうございます
Okay.
は
Okay.
い
Okay. I share again. Oh, sorry.
Okay, we can see.
Can you see? I can't see my PowerPoint.
Yes, 見えます。
見えます？
はい。
I can't
どう
see.
ぞ。
I can't see. Why? Why? Why I can't see my PowerPoint?
Is the PowerPoint is the first slide now. We can see
Mhm.
your PowerPoint
Yes.
already.
Yeah. Wait a little bit. I can't see my PowerPoint. Why?
Maybe closing and then share again.
Okay. Close. Share. Close. Ah. Mhm. No. Where? Why? 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 Once I quit share
Yes,
and
and share again.
okay. Okay.
Okay, I can see now.
Okay.
Yes, thank you very
So,
much. Sensei.
thank you. Thank you very much for very, very good introduction for me, Professor Sorapon. Thank you, and many other audience coming here to hear my talk. Now, I'll talk about polymer physics, especially molecular motion and the properties of non-crystalline solid. First of all, I want to introduce myself. I have been professor mainly in, I read this sentence. Education and research field of physics with more than 40 years, because I'm now age is 70 years old, in university and other higher education school. And before professor, I was a researcher in the laboratory of the company in the field of polymer product in Tokyo. And my academic work have focused on polymer physics, the education of physics, and the education of a person with global competencies. Okay. Academic background of me, such kind of first bachelor in applied physics, Hokkaido University, Department of Applied Physics, Faculty of Engineering. After that, master course of that university, and doctor course at that university. I summarized my experience. I explain next slide. First, after graduation doctor course, I worked as a researcher in this company, It's located Tokyo, center of Tokyo. It's buildings of that company. And next, I moved to National College of Technology, Japan. It's located, some city, name of the city is Tomakomai. It's located here. Can you see my mouse pointer?
Yes,先生、見えます。
Jet.
どうぞ、
Red,
あの、
red mouse pointer. Can you see?
続くしてください。はい。
Yes.
OK です。
Yes.
This college, a national college, and during that college, I visited 1 year University of Tokyo, a researcher abroad program, Ministry of Education, Culture, Sports, Science, Technology. At that time, I back to Tokyo again. And after that, I moved to Hokkaido Information University up to last March. I retired March this year. And during professor of Hokkaido Information University, it's abbreviated HIU. I was visiting professor of Université Claude Bernard Lyon 1, Lyon en France. It's a picture website of that university. And it's located here, France. And UCSI University Kuala Lumpur in Malaysia recently. These are here. It's the next country to Thailand. And so that is my career. And research field is polymer physics, education of physics, education of a person with global competencies. And education fields also physics, information science and technology, global competency. Education of global competency. Now, RMTT student now came to Hokkaido Information University, HIU, and take part in workshop with HIU students. HIU students. I shortly explain my previous university, Hokkaido Information University. This is the landscape of Hokkaido Information University. I think it's smaller than RMTT. RMTT is a very big university. HIU area is, it's a dormitory. It's a laboratory of ICT, and it's another laboratory here. This area is Hokkaido Information University. This forest, not our area. And it's Bangkok. In Bangkok, Sukhumvit, there is a buildings of JSPS. JSPS means Japan Society for Promotion Science. It's a Bangkok office located in Sukhumvit, in this building. In this office, many Japanese universities poster presented. HIU poster is also presented in this office. If you have a chance, please go to that office and look this poster. HIU located here. It's Hokkaido Island. This is Honshu Island, Shikoku Island, Kyushu Island. This Okinawa. There is no island, North Island. Sapporo City is a very big, one of the big city in Japan. And HIU located near Sapporo City, Ebetsu City. Ebetsu City. By train from Sapporo Central Station, 20 minutes. It takes 20 minutes to station of this city. Okay. Hokkaido Information is one of the group organization. This group has 10 computer school, many places in Japan, and the headquarters of this group located in Tokyo, and three companies, such kind of company. Third one is space engineering development. That one of that company, that one of works that company to control satellite or Japanese satellite software. Okay. It's a space engineering development company. So I finished my presentation, and I a little bit different. Now I finished introduction. Now, maybe I will change a little bit this content. Sorry. First of all, introduction. I think there are some students, so I want to recommend the students. I recommend not to learn knowledge, but to learn how to obtain knowledge about science and technology, as well as mastering fundamentals of your major field in your university. But don't misunderstand me. I emphasize not only not only knowledge, but also how to obtain knowledge and mastering fundamentals. Learn knowledge is important, but how to obtain knowledge and fundamentals more important, I think. Because people have developed science and technology over very long period in human history. Humanity has accumulated enormous amount of knowledge, but has been filtered through course of history. Finally, at present, we have only a few percent of them. It's a very short history of focused on polymer physics. Polymer physics started by findings of fiber structure by X-rays, and Staudinger found the concept of polymer, large molecule, and after that, many physical findings, important findings. Those are very important fundamentals for polymer physics. But there is more knowledge behind this knowledge. This knowledge has filtered through course of the history. Behind this knowledge, there were enormous amount of papers. For example, this is some paper. Unfortunately, it's not mine. I found it this morning in the website. This is the reference of this paper. Many references, but I want to find it's very small, so very small. So I zoom, for example, around here. Oh, I hope you see a year. This paper, 1978. This paper, 1979. Not a new one. Other papers, a new paper also. And here, 1998. Here, 1987. Here, also, not a new one. Some paper survive in the history, in the course of history. But many papers will be many researchers forget about it. That's why I recommend the students to learn not only recent knowledge, but also fundamentals, very important, historically important papers. Anyway, these are application of polymers. For example, I think it's absorb vibration of earthquake. I think Thailand, not so many earthquake, but Japan, we have a lot of big earthquake. So buildings avoid dangerous, destroy. Recently, many buildings, there is something like that. It's a rubber, special rubber, absorb vibration of earthquake uh, to avoid break the building. And tire is also rubber, it's polymer. And airplane, it's some Boeing 787, maybe. Body of airplane is carbon fiber. And the sports, there's many polymer materials. And it's a electronics device. To make this device, there is a photoresist or something like that. Many things for application. But as I said, I worked in laboratory of company long time before. I had a job of development, new material. At that time, I made practical research, of course, but such kind of practical research, fundamental research is very important. For example, my experience as a researcher in the company, at that time, my project team was given theme, development of a rubber-like material, which slips smoothly on the surface of glasses. That material used for a window of the car. This is a glass window, and I think you could find you you watched that thing. I'm not sure. Here, there's a rubber-like material to touch glass to avoid water rain inside. But rubber-like material is not slippery against glass. So long time ago, this material, this stuff, this things, cross section here. I zoom here like that. Long time ago, for slip easily against glass, this rubber-like material, surface of material, there was a hair, short hair, many short hair to slip smoothly. But such kind of thing, if rain penetrate here, it's a difficult problem. So that's why we need to develop without hair, but slippy against glass. So our team developed such kind of one. At that time, these practical research, applied practical research, we made experiment of coefficient of friction for many compound, many material, test material, and measure coefficient of friction, which one is slippy. But for that, we need to understand mechanism of friction. Mechanism of friction, one of that is, of course, surface uh, shape, very small, microscope level, small surface shape. But not only that, energy loss is cause of friction. Energy loss, that is two kind of energy loss. One is surface energy loss. Another one is internal friction. Internal friction problem is very intrinsic problem of polymer material. So I want to say to student, behind practical research, you have to use fundamental knowledge. I think it's important from my experience. Okay, let me move to today's topic, polymer physics. For example, it's a solid polymer electrolyte. Recently, battery, lithium-ion battery is used in many electrical apparatus, smartphone or something like that. PC, computer also, such kind of battery. Such kind of battery recently, solid polymer electrolyte is researched. Many researchers research polymer electrolyte. This is electrode to electrode, plus and minus, and between here. Normally, before this electrode material is liquid electrolyte, but recently many researchers research polymer solid electrolyte. In here, ion, mainly a lithium ion, for example, moves through from here to here. Solid, in the solid, it is normally difficult to pass through ion. In that case, we have to research many problems. As I explain later, polymer material, solid material, has a structure of like this. It's a crystalline part and a non-crystalline part. And I will move some free space. That's why such kind of, where I will move through, how I will move through, what is the velocity of ion move. Such kind of thing is a very important issue to develop polymer electrolyte. That's why important thing we have to consider. For example, ion motion, polymer chain motion, and solid structure of polymers. Such kind of issue is very important to consider ionic motion. It's a fundamentals. As I emphasized today, it's a fundamental knowledge. So now let me introduce some of fundamentals of polymer physics. Fundamentals of polymer physics is a huge, enormous things. So today I don't have a lot of time, so I shortly one of fundamentals of polymer physics. I'll introduce that. First of all, what is polymer? Polymer is non-crystalline solid intrinsically. Some polymer crystallize, but I explain that later. But intrinsically, polymer is non-crystalline. Non-crystalline, or we call it amorphous solid, that is, atoms and molecules do not organize a definite crystal lattice. Small molecules, maybe even though there is a defect in the crystalline, but intrinsically organize definite crystal. Small molecule make definite crystal, but polymer do not organize a definite crystal lattice. And that consequently, there is structural short-range order, but not long-range order. It's a word. I'd like to explain about the word. Amorphous. I use a non-crystalline solid, sometimes use amorphous. Amorphous is a plus morphous. Morphous means capable of making a form. A means negative. That's why amorphous is same as non-crystalline. Non-crystalline amorphous state, for example, glass, plastic, rubber, gel. Those are name of the state. And polymers make these states. And let me emphasize these things. Polymer is a model system for time-dependent phenomenon of a material. Time dependency is very important concept of polymer physics. Physical phenomena of materials show characteristic time. We call it relaxation time. A polymer system has long relaxation time. But a small molecular system has short relaxation time generally. Although the phenomena with very short tau, the small molecular system, is difficult to investigate because the phenomenon, time-dependent phenomenon is need very, very short time, so we can't investigate that process. But it could be easy in the polymer system because relaxation time is long. That's why we can investigate time-dependent phenomenon precisely by using polymer as a model system. I said, I already explained this one. Move to next slide. Okay, I summarize maybe every student knows such kind of thing very well, I think. But I summarize the basic knowledge. Polymer, in other words, macromolecule. For example, this is a polyethylene, small molecule, monomer, it's ethylene, synthesized to such kind of polymer chain, very long, several, in some case, several 100 nanometers. It's up to approximately 0.1 micrometer if we elongate that, stretch that. Thickness over here is 50 to 100 micrometer. That's why length of macromolecule, polymer molecule is very long. But such kind of long molecule normally coiled state. So occupy small volume. Now we want to consider about expansion. Heating metal, liquid, gas, such kind of image. Before heating, of course, each molecule or atom move thermal motion at, at that temperature. And solid is rather say vibration at that temperature. And the liquid, not the vibration, maybe it's move. And gas move faster than liquid. It's a high school student knowledge, I think. But heating those state, solid vibration, each atom or molecule vibration is intense. And the liquid velocity of move increase, of course, and the gas more rapid. As a result of that molecular motion, body of material is expand. As a result of motion is activated. That's why, so that body expand. So as I explained, for example, metal, if we heat metal, volume increase. Now I'll give you some question. This is a rubber band. Rubber band, I think everybody know rubber band, rubber. Maybe usually use natural rubber. When we heat rubber, it's elongate or contract, shrink or extend. I hope you consider about this. 5 seconds. Do you have answer? Okay.
Yes.
So
Okay, please continue. Just state.
Okay, I'll continue.
Okay, Sensei, thank you very much.
Wait a little bit. I change share. Where is? Maybe here. Oh, sorry.
置いてないです。少し。Okay, 多分。
Okay. Huh? Excuse me. Sorry. Hmm? Wait a little bit. I'm sorry.
Okay.
Can you see?
I can see just only the picture of your picture here, not moving.
Okay, I
This
do it.
is more than 5 years.
Can you see?
Yes, okay, I can see.
Can you see my movie? He now explaining. He explained. I start
The rubber.
experiment. Rubber band. He put something to expand rubber. He said, when we heat it, what happened? He put the scale here for easy to observe length of rubber band. First, 30, position of 30, and he heat it by hair dryer. Sound of hair dryer, and end of rubber band here, 5 millimeters shorter. Okay. Consequently, if when heated, rubber band contract, shrink. It's different from usual low molecular weight material. Why does that thing happen? Polymer is such kind of molecule, and molecule, of course, move at that temperature, and I think you suppose there are many child, hands on hand, hold hand each other, and they move different direction. They want to go. At that time, in that case, maybe this you think this blue particle is child. Each child move different direction. Maybe a circle of the child smaller of contraction of rubber band. When heated, molecule shrink. That's why rubber shrink. It's very intrinsic properties of polymer material.
先生、
はい。
ちょっと待ってください。今、スライド、まだ見えてない。
見えてない？
here.
You can't see?
Hello, Sensei, I'm Bunyang.
今見えない。
Okay, nice to see you online. Okay, but your slide is not shared yet.
先生、もう一回スライドをシェアをしてください。もう一回消して。
もう一回ね。
もう一回消してください。
Excuse me. This one?
Okay, we can see your slide now, Professor.
You can see? Okay.
Yes. Yeah. Very
มา
nice to
ถึง
see
ก็
you
เสียงดัง
online.
เลย
How
นะ
are you? สวัสดีพี่เต้สวัสดี
Booyah,
ครับ
booyah.
Okay. I just come to say hello and then I have to quit.
Hello, how are
Okay.
you?
Thank you very much. I hope to welcome you in Thailand.
You drink every night.
Almost every day. Okay, you know me. Thank you, sir. Okay, thank you very much. So
Oh,
you can
okay.
continue. So thank
Okay,
you.
okay, I'll
One student
continue.
also who joined everybody here. So
Yeah.
Professor Yuichi Anada, he is
Yes.
the professional in the field of polymer. So it's really really great to have you here. So please continue. Thank you.
Thank you so much. Kind introduction for me.
Again. Okay.
Okay, I continue. I'm very sorry. My slide is not seen. I explain again. Why rubber band shrink by heating, and polymer is like that, and move thermal motion, and each polymer unit move different direction. I suppose you suppose a child if these blue circle is child and the child hold hands each other and the child move to a direction they want to move. In that case, child move many direction each child. So this circle finally small circle becomes small circle. And polymer motion, same thing happens. It's a reason of shrink of rubber band when heated. So that phenomenon is very intrinsic reason of character of polymer material, polymer molecule. So I summarize again. A normal material, when heated, expand, volume increase, but polymer, when heated, volume decrease. Normal material, this elasticity is energetic elasticity, but polymer, it's entropy because of entropy, result of entropy change, so entropic elasticity. So let me move to shortly about the structure of a polymer solid. Polymer intrinsically make amorphous state, but some polymer make crystal, but it's make not a definite crystal because polymer is a long chain. Crystal structure of polymer is like this. It's found by this microscopic image. Long time ago, it's a very important scientific paper. But as a result, now we understand polymer crystal is of this crystallite, normal crystal. It's make a unit cell of crystal. But surface of this crystallite, polymer chain fold. It's not crystal. And end of polymer, for example, here, it's not also, it's like an amorphous state. So polymer crystallite is core normal crystalline part and surface non-crystalline part. We call it lamella. And this is single crystal. We call it a single crystal lamella. But normally, polymer material, these lamella accumulate and make spherulite. Spherulite is, what is spherulite? That is, this illustration in the show that image, these lamellae, and sometimes many polymers between lamella, non-crystalline polymer chain. It's a normal state, and lamella is accumulate like that. This is spherulite. We call it spherulite. The many spherulite accumulate and make material, normal polymeric material. Then we move to physical properties of polymers. And first of all, I explain about glass or crystal. This figure shows vertical axis volume and horizontal axis temperature. The melted state, from melted state, normal low molecular material, when cooled, some temperature, it's a crystallization temperature, normal material crystallize, make phase transition, and change to crystal structure. But polymer, it's difficult to crystallize, is generally not crystallized here, and volume decrease continuously, and at some temperature, rate of decrease smaller. In this state, polymer molecules move very, very slowly. This state, we call it glassy state. That is to say glass. And this temperature is called glass transition temperature. This is the property of polymer material. And polymer material, polymer molecule move fast above glass transition temperature, but it shows very around here, a remarkable time dependence here, and motion of the polymer is very, very slow. Now, I'd like to explain very important concept of polymer physics, free volume. Free volume, what is free volume? It's a similar graph as before, previous slide. Volume, temperature, glass transition temperature, total volume of material expressed by this line. It showed it V. And this lower line shows occupied volume. Occupied volume is volume of molecules. That is to say, van der Waals radius, plus volume associated with vibrational motion. So I explain this concept by this figure. Blue one is van der Waals radius, and the polymer moves thermal motion. This is a small molecule. It's a polymer molecule. And this area is occupied volume. But be careful. Occupied volume is defined by vibration area, it depends on temperature. That's why occupied volume is definite definition, is not a definite definition, ambiguous definition. It's a very important point. And free volume. Free volume is difference of two lines. So that's why free volume, VF, is total volume minus occupied volume. That's why free volume, definition of free volume is also not a definite definition, ambiguous definition. It's an important point. So, I explain additionally a little bit about crystalline solid. Some polymer crystallize in that polymer from melting state. When cooled around some crystallization temperature, it moved to crystal lamellar state and semi-crystalline state from here. But some molecule not crystallized show glass transition. It's a very complicated material. It's like this. So, as I explained, physical quantities of a polymer strongly depend on time. So I explain about this slide, time dependence of properties of a polymer material. This graph show if we give strain to polymer material, constant strain at one time here, no stress here, at one time we put some strain and keep strain, that strain. At the same time, stress in the material. First, when a strain input, stress is big, but its decreases depend on time. So it's a relaxation phenomena. That is to say, stress depends on time. This curve, it's a time for decrease is characterized by relaxation time. And for such kind of property, we make this model, explained by this model. It's called Maxwell model. It's this part is spring. This part is dashpot. It's a oily, viscous thing. So if we give strain each end, first, this spring expand. But at that time, this part not move. But in time, spending time, this spring gradually shorten, and this part, oily part, gradually move up. Strain is constant. That's why stress is decreased. If you see my small face, it's a Maxwell model is like this, spring part and a oily part. First, we give strain, this thing, each end, First, spring expand, but gradually spring shrink, and dashboard part move and become long. So this is a property of polymer, physical properties of polymer. And so in this model, stress was determined by strain times modulus. The modulus depends on time. Stimulus is stress. Stimulus, strain is stimulus, and stress as response. And modulus is mathematically same response function. So if we change this equation, modulus expressed by this equation, and this is a response function. In this case, relaxation time is one single relaxation time. Such kind of model is called Debye type model. If we give strain sinusoidal, in that case, it depends on frequency. Time dependence is also changed to frequency dependence. In that case, response function expressed by such kind of equation. But I explain this a little bit. Next slide. I explain very shortly about this. This phi t is decay function. Decay function is time change of response function, in this case modulus, and Debye type relaxation. This decay time scale is single, only one. In this case, this response function expressed by like this, and real part and imaginary part. This is very important. Imaginary part is a physical meaning is storage of energy. And imaginary part means loss of energy. We have formalism of response function. I explained now modulus as a response function. In this case, stimulus strain, stress as response. If we change inverse, stress as stimulus and strain as response, in that case, response function is compliance. On the other hand, electrical properties, if stimulus external electric field, response is electric displacement. In that case, response function is dielectric constant, but it depends on time. We normally call it permittivity. And if we change stimulus and response like this, electric displacement as stimulus and electric field as response, in that case, response function is electric modulus. If we research ionic motion, this quantity, electric modulus, is very important quantity, very important tool to investigate ionic motion. Maxwell model relaxation. as I said, it's a single relaxation time. In this case, as I explained, the real part and the imaginary part is expressed like this. As I explained in the graphically showing, imaginary part show such kind of peak, and real part such kind of stepwise change. Horizontal axis frequency and vertical axis is modulus. And as I explained, this imaginary part, this under this curve, this area shows energy loss, internal friction. But normal observation on polymers, it's some example of polystyrene. Vertical axis is modulus, real part, imaginary part. Horizontal frequency. This imaginary part, open rectangular, shows peak, but width of this peak broader, very broader than Maxwell model relaxation. It's normal for polymer material. So how we explain this phenomenon? Normally, there's some explanation, but one of important explanation is a system has multiple relaxation time. For example, combination of several Maxwell model. Each model have a relaxation time. So this system has many relaxation time. That's why this curve broaden. I explained very shortly about this. Distribution of relaxation time. And normally we use relaxation spectrum in this equation, and relaxation spectrum by relaxation spectrum, we investigate distribution of relaxation time precisely. Anyway, let me move to ion motion in polymer solid. Example, as I show this slide before, when we investigate lithium-ion battery solid polymer electrolyte in here, in that case, we have to investigate not only ion motion, but also polymer chain motion and polymer structure, solid structure of polymers. We need to investigate these issues. These are fundamental I explained, I emphasized. To investigate ionic motion in polymer material, we use usually permittivity here, horizontal is angular frequency also, permittivity or conductivity. Of course, it's a high conductivity is good material for polymer electrolyte. And additionally, electric modulus. Normally, investigation of ionic motion in polymer, many researchers use such kind of quantities. And high frequencies, we can observe dielectric relaxation. Dielectric relaxation is originated from polymer dipole orientation. And lower frequency, here, we can observe DC conduction. It's originated from ionic motion in long distance. And the lowest frequency region, we observe electrode polarization. It's not the intrinsic polarization of polymer material because it's a polarization between electrode and surface of the polymer materials. But sometimes when we make experiment, sometimes this electrode polarization cover information of DC conduction. So we want to avoid this electrode polarization experimentally or analytically. This is the example of some paper. Here, it's a permittivity, real part of a permittivity here, and this curve conductivity, this scale, and permittivity, lower frequency region, we observe electrode polarization. But if we change this quantity to electric modulus M, this electrode polarization area is here. And the imaginary part of electric modulus show such kind of peak, and the real part stepwise change. And in this analysis, we can see no electrode polarization. That's why we use electric modulus, we can obtain accurate information of ionic motion. In this paper, author find inhomogeneity of ionic motion of this material. If ion moves through in the material, some free space but some free space is homogeneous. Free energy barrier is homogeneous like this. But if ion move free space, next free space, there is inhomogeneity. Free energy barrier also inhomogeneous. In that case, time scale of jumping is inhomogeneous. This researcher found inhomogeneity of this material from this data, analysis of electric modulus. This is the result. They found two kind of relaxation time. We call it ionic motion relaxation time. We call it conductivity relaxation time, like this. So we can find precise information about ionic motion. This is another example. This author find minimum free volume ion jump into from conductivity data. And this is a little bit a new one. This author investigate where ion moves through. As I explained, polymer crystal is composed of lamella, and the lamella is composed of core crystallite part and surface non-crystalline part. Ion located, this author found ion move interlamellar amorphous region and they make a very special specimen, very oriented thin film, and they found like this. It's my work. It's a old paper. I made research about polyvinyl chloride with polypotassium blend, and I also use conductivity electric modulus and analysis of electric modulus. I found there's a two kind of ionic motion. One is originated from inside a polypotassium particle, and another ionic motion is boundary of polypotassium particle and polyvinyl chloride. And another one, and I also analyze left-hand side is a result of isotactic polypropylene. I also use electric modulus and low temperature. Ionic motion is single relaxation time, but temperature increased, higher temperature, there appears another relaxation time mode of ionic motion. And this is also for low density polyethylene. And I also find there is two kind of ionic motion, and it's related with microstructure of amorphous region between lamella, I suppose. This is recent results. Plasticized polyvinyl chloride. I estimated the free space where ion can move into. And this is the experimental result of conductivity. And the center figure is permittivity. And the right-hand side is modulus, electric modulus. And I analyze mainly electric modulus. So such kind of model, I found finally radius of free space where ion can move into minimum size is like this. So this is today's talk application to if we apply a physical polymer physics to especially ionic motion, we can find such a kind of things. It's a apparatus of my lab. It's actually I don't have this one now, and the programming for measurement. Okay, thank you for your kind attention. It's the end
Thank
of
you
my
very much,
talk.
Sensei. Very,
Thank you.
very nice presentation and easy to understand. Okay, now it's time for question. Any question from the floor or the audience? Any? So this time for ask the question. So please.
Any question about
Thank you very
myself?
much, Professor Ananda. It was very good, very informative. I have a question about the electrolyte polarization. What are the primary causes that happen for when we have electrode polarization?
Excuse me, could you explain point of your question again?
About the electrode polarization, because we should
Yeah.
avoid the parts,
Yeah,
right?
yeah.
Yes. So I'm looking for yes in the back. Yes. So I'm looking for what are the primary causes that this happen and how we can
Uh-huh.
avoid it in general terms.
Because electrode polarization originated from the electric charge between surface of material and surface of electrode. It's not depends on properties of a material. We need information about the properties inside the material, but
Mhm.
this electrode polarization doesn't have such kind of information. But for example, permittivity, real part of permittivity, because of electric polarization, it's a increase. It's a ideal illustrate, but for example, here, this is electrode polarization. This
Mhm.
cover, here is information. This part is include information of DC conduction, this,
Mhm.
or permittivity, but it's cover. And we can easily understand if we change electric modulus.
Mm.
From same data, we can analyze electric modulus. In this case, electrode polarization, this area, the intrinsically permittivity and modulus have same information, but
Mhm.
we use by this data, we can avoid electrode polarization. That's why we investigate precisely about ionic motion property.
Mm.
It's okay.
Oh, I see. Yes, sir. Mhm.
So
Understood.
many researchers of ionic motion use, especially European researcher, United States researcher, uh, use electric modulus since
Mm.
long time ago. This
Oh.
paper, this paper is a very important paper for using calculation. It's not a material is not a polymer actually. It's not a polymer but a glassy state material. It's
Mhm.
very
Oh, I see.
important paper. Old paper, but a very important paper.
Mhm. I see. Understood. I see. Thank. Mhm.
Any other?
Yes, thank you very much. Yeah,
Thank you. Thank you. Very good question.
yeah, thank you very much.
Is there any question? Not only research, but also about myself. Any question?
About yourself, you should have tell us your secret.
Secret. Secret is a secret.
Oh, why?
Okay. Okay. I open my secret. Mm. I have many hobby. Many hobby.
Oh.
one of my hobby is sports, triathlon.
Mm-hmm.
Have you
Triathlon.
triathlon?
No,
Uh,
that's
Triathlon is swimming and
hmm.
bicycle and running one day.
Oh, I see. So all of them are cardiovascular sport.
Mm. At the Olympic game in Paris last month,
Mm-hmm.
triathlon game was held in River Seine, very dirty water Seine. They swam in the Seine River, and
Mm-hmm.
after that, bicycle and running. And
Yeah.
another another sports hobby is cross country ski. I'm
Oh,
sorry, Thailand, I think no snow, so it's difficult to do that.
yeah.
Hokkaido area, winter season, we have a lot of snow. Cross country ski is by ski like running, and
Mm-hmm.
mountain is a mountain. And I have another one, not sports. Thai professor don't know about my hobby, this hobby. Can you
Mm-hmm.
see this picture?
Yes, it is. Yes, I can see.
You can see? It's I
It is
painted.
like garden, trees, garden, something like
Yes,
this. I see. Yes, yes.
yes. The Montmartre, Montmartre, Paris,
Oh, Paris, Montmartre.
Paris. Yes, it's my signature here.
Oh, I see. Oh, now I see.
I painted, and it's French. Can you see?
Yes, la poudre Montmartre que ma place préférée, something like
Ma
yes.
place, ma place préférée, je veux conseiller le visiter.
Hmm.
It's also my hobby, French.
Oh wow. Oh, another language, another
I wrote
country.
this phrase.
Ah, I see. What does it mean, this phrase in English?
Ah, and this means it's a hill, first phrase, hill of Montmartre. This is the place which I like. I prefer.
Ah,
I prefer.
mhm.
I recommend you, final phrase, I recommend you to visit this this hill, Montmartre.
Oh, I see. I see. That's beautiful.
Mm. Okay.
Nice, nice. When was the last time you have been in Paris?
Uh, Paris, last year, last February, my
Hmm.
last visit,
February.
Paris, winter. It's also, I wrote it.
Mm, I see.
Can you
Yeah,
see?
that's the kaki fruit.
Fruit. It's a Japanese, maybe original fruits. Persimmon
Mm.
in English.
Oh, yes, yeah, persimmon,
Mm.
persimmon.
This fruits was I put it from my garden.
Hmm. Oh, wow. Yeah.
So I have many hobby.
Yes, yeah. Gardening is a very good
Mm.
hobby, I think.
And I like drinking.
Ah.
Solapom Bunyan like
Yes,
drink also.
Yeah.
yes, very good. It's good for connection, Sensei. Is the liquid is not
Mm.
solid and This one is for the catalyst of our connection.
Yes, yes.
It's good
Strong
for health.
connection by alcohol.
Good for health, right?
Yes, it's also good for health.
So if don't have the question, my question is how can you have your very strong health like this?
Very strong health?
How?
How?
The secret.
The secret.
Secret
The
is
secret.
secret.
1, 2, 3. How? just three point of your very
3 point?
strong health. Yes.
Training. First point is training.
Training.
Second
right.
point, training. Third point, training.
Training. Many training. How about your food?
Training. I go to gym 2 or 3 times a week and training.
Oh, I see. Bench press.
Yes.
Yeah.
And running, swimming in the pool every week. And winter season, every weekend, I do cross-country ski training.
Oh, that's
And
beautiful.
every day, every evening, I drink beer. I think it's very good for health. It's one of the training.
Yes, that's fun. That's a fun secret.
Secret. I open secret here.
Thank you very much. Yeah, for sure. We will use it.
I want to drink Shinha Chan Leo in Thailand.
Oh yes, yes. Which one is your favorite, sir?
Shinha. Shinha. Next to Chan. Next to Leo.
Oh.
That's everything I like.
Awesome. Great.
Okay, Sensei.
Yes.
Any question?
Any question
Any
from me?
question? Any question? If don't have the question today, on behalf of Faculty of Engineering and this course of the Energy and Materials Engineering in PhD course and also the master course of Material Engineering. So we would like to say thank you, many thanks. Thank you very much for very kind of your presentation and very kind of your explanation and also this seminar, Sensei.
Thank you.
So we
Thank you
hope
so
that
much.
our students can get your knowledge and apply this knowledge for polymer physics and apply for their research. Okay.
Thank you.
So thank you very much, Sensei.
You're welcome.
Thank you very much, Professor
Yes.
Anand. Thank you very
Yes.
much.
Thank
Yes.
you. I hope the
ありがとうござい
students
ます。
do very good work.
Yes, yes. ありがとうございます。どうも大きに。どうも大きに。
関西人。
また来週です、先生。
はい、来週ね。
はい、また来で。
来年。
はい。
来年。
また来で。先生
来年
โอเค ขอบคุณนักศึกษาทุกท่านครับ ขอบคุณอาจารย์ทุกท่านครับแล้ววันนี้หวังเป็นอย่างยิ่งว่าจะได้ความรู้แล้วเราเอาไปแอพพลายใช้นะครับครับผม
Thank you very much.
Thank you.
ครับขอบคุณครับ Thank you very much 先生どうも大きに
Thank you very much.
はい
So, I will go out.
Okay
Have a good day, sir. Have a good day.
Thank you. Bye bye.
Thank you นิมาบ๊ายบาย
Thank you.